As we alluded to already, Charney, a brilliant scientist who contributed so much, was working without tropical data and assumed tropical motions of the order of 10 to the 6 in the horizontal, 10 to the 6 meters in the horizontal, and had some difficulties in interpreting how you would generate motions in the tropical atmosphere, the dynamics. Okay, so some of the early interpretations then can be looked at in terms of the vorticity equation. I hope you have a good sense of vorticity. Okay. If you, for example, if you're on a merry-go-round, you are going around, but if you stay long enough and get off, you will begin to feel dizzy. So your brain has acquired some tendency to rotate, which is vorticity. I'm just giving some weird example, but if you put a paddle and its tendency to rotate around its axis is in some sense, well, that is the vorticity. So how do we do that? Basically, you take the cross product of the momentum equation again, writing in vector form. Rho dv dt is the pressure gradient, gravity, Coriolis, and dissipation forces. The vorticity here is written as curl of v. So that's the tendency to rotate. This is referred to as relative vorticity because, as we said, just being on the rotating framework, we are on a merry-go-round, so we are acquiring vorticity, a planetary vorticity anyways, and we can have our own vorticity on top of that. So total vorticity will be zeta plus f, where f is the planetary vorticity. So essentially you end up with this total vorticity equation, which has the advection term and the other terms of divergence of the flow, stretching and compressing the vorticity, vertical stretching term, and the vertical divergence term you can think of. There is advection or divergence of planetary vorticity, so like a Rossby wave, which is sitting somewhere with the planetary vorticity that is local f, and then it's pushed or perturbed to move to another f, then it is carrying some planetary vorticity with it, and of course the divergent flow is being affected by the planetary vorticity itself, which is equal to the famous baroclinic term we looked at, baroclinicity vector, that we looked at in terms of grad rho cross grad p. Here we are dividing by rho, taking the rho from this side and putting it over here. Complex looking equation, but essentially in terms of dynamics, when the fluid is moving, we said that the atmospheric column can be seen as vortex tubes. So divergent and convergent flows and advection of the air masses can stretch or compress the vorticity tube and can tilt it and do all sorts of things. And you can imagine a skater ice skating and then expanding the arms to slow down, bringing them together to speed up, and so on and so forth. So ice is very smooth, there is not much friction, the blade is very sharp, so they can easily change their rotation rate by changing the inertia around the axis. So this is kind of those terms: stretching, advecting, and so on. Okay, in general, just taking these terms, we are going to scale them. The term here is order 1, and the other terms are scaled in terms of, again, horizontal and vertical motions and scales of spatial scales of motions, along with the rotational terms. Rossby number obviously comes in, Froude number comes in, and for Rossby number much less than 1, the extratropical system, we still have the vorticity term being 1. Then you have Richardson and Rossby numbers resulting in order 10 to the minus 2. 2 omega L squared over UA cosine phi term depends on what motion you are considering, and then this is again Ri times R0 squared term, and then Froude number divided by Rossby number squared term. So we're taking the complex looking vorticity equation and trying to see what happens in the extratropics as flow and baroclinic instabilities are moving energy from PE to KE, or the atmosphere is hitting a mountain, rising over it, getting compressed, and then coming down on the other side. All kinds of things happen. For the tropical systems where you have Rossby number order 1, again you have terms that go from order 1 to 10 to the minus 3, and this term that we hold on without any specific scale or magnitude, because it depends on which particular part of the system you're considering, and Richardson number and Froude number. Okay, so go to the vorticity equation then for the extratropics. The balance will be between this time variability and advection term with the divergence term. Okay, I hope you can get an intuitive sense for these. Sometimes even I feel like I don't have enough intuition about these, because you have to work with those atmospheric dynamics long enough to have a very good intuitive sense about which terms these are. So that balance ends up being 0 for the extratropics with the spatial horizontal scale of 1000 kilometers, 10 to the 6 meters, not kilometers, and Rossby number is much less than 1. Looking at the tropics, the continuity equation can be simplified as we saw before, du dx plus dv dy equal to minus d rho 0 d w divided by rho 0 dz. So it's the advection of the background density. If you imagine a stable stratification and you have vertical motions w of the scale of w, then the vertical velocity will be carrying the background density as it moves from one height to the other, which is going to perturb the background profile, which is going to generate horizontal divergence and convergence. Okay, use that into the vorticity equation, then the balance is going to be just the advection term being 0. The time variability is basically going to come from vorticity tubes moving and converging and diverging. Okay, very different balance than here for the extratropics, where you had the flow itself. Because it's baroclinic, it was carrying the flow divergence was transporting vorticity and able to affect vorticity balance, whereas here, if Rossby number is close to 1 and the motions of order are of the order of 10 to the 6, which is what Charney had assumed, somewhat erroneously because he didn't have data, then he got stuck with explaining the motions. That balance is going to create a problem. Whereas if you go to the scales of divergent motion in the tropics, which are things like the monsoon, the Walker cell, we will talk about it in more detail when we come to El Nino, or the Hadley cell, which we will talk more about when we come to the dynamics, and things like MJOs, Madden-Julian oscillations. They are order 10,000 kilometers, not 1,000 kilometers, and there they are able to produce and store potential energy and so on, and they are going to have a balance that is very similar to the extratropics, and there the Rossby number is less than 1 at those scales. Then it becomes easier to explain the tropical dynamics and the tropical motions. So this assumption of the scale led to some issues in explaining how vertical motions can be created in the tropics. So this is just looking at that quickly. In a barotropic system in the tropics, the flow is non-divergent, so you have motion in the upper atmosphere and the lower atmosphere that are basically disconnected from each other. Whereas in the extratropics, you have divergent motions, so that's where the verticity balance we looked at comes from. That's the horizontal scale, that's the Coriolis, and that's the scales of motion with Rossby number much less than 1. So this gives you a coupling of the lower and the upper atmosphere and the conversions of potential energy to kinetic energy and all these rich scales of motion that we talk about. But in the tropics, if you go to 10 to the 7 meter scale with the Coriolis and horizontal motions of the same scale, then you end up producing divergent motions. Obviously, Walker cell and Hadley cell include lots of large-scale divergence and convergence. So do the monsoons, so do the Madden-Julian oscillations. So the restriction of a barotropic system not creating Ke from PE gets released when we use the proper scales of 10 to the 7 meters. Okay, let's leave this here and tells you about the interpretation of the scaling when we use verticity. Verticity is a very rich concept. Hopefully you can read up much more than the kind of fast route I took here, but we will come back to this later on in terms of verticity equation and the balance of terms.